Hey guys, Chris Brew here. We're gonna work together to learn how to solve an easy leak code problem. It's just actually not that easy at all. You can judge for yourself if you would consider this an easy problem. Uh, yeah, a lot of people thought this was pretty hard, but it might be because you have to do you have to know your bitwise operations. And if you're throwing a question like this in an interview, you don't want to be the guy that stumbles and doesn't know what the heck to do. So we're gonna work together to solve this problem. I'm gonna show you how to solve it. But first, I'm gonna show you how to use the bitwise operations before we even get into solving it. And then once we know those, we can go into solving the actual problem. So let's jump right in. Okay, one more thing. If you already know the basic bitwise operations, then you can go ahead and skip to where I actually solved the leak code problem, but otherwise stick around. Let me read to you the actual problem here. It's number 190, reverse bits. Well, reverse bits of a given 32-bit signed integer. Okay, so just reverse the bits of a 32-bit signed integer. All right, easy enough. If we have 432615596, we get this, which is, notice that this is not actually like this number in reverse. That's not what's going on here. Well, it might seem like way from the question, but actually when you reverse the bits themselves, the number, pretty random number actually, and you can't really like arithmetically figure out what that number is. Like you basically have to reverse the bits to find out what that number is. And so, okay, so this is the problem. To know how to solve this problem, we have to know what the bitwise operations do, and we're going to be working in Java. So before we jump into solving the problem, let's just write some comments here. We're going to give an example number to work with because using an example makes it way easier to understand what the heck is going on. How about we just do 1011 as an example, right? And if we wanted to do a bitwise operation on it, here, let me just make a public static void main string args. Let's make a main function real quick, and then so the first bitwise function we want to learn is a shift, bit shift. So we go in here. And the way to do that is you have these two carets pointing that way to the right, and it's a right shift because they're pointing that way, you know? And so we can do something like this, right? In Java, we can say 8 and we shift that to the right once, and then that gives us a new number. So I guess we have to like assign it to a number like that so Java isn't upset. But yeah, so we get this new number like that. And actually this number is okay, wait. This is 1 plus 2, so it's 3, and there's no 4 here, so it's 11. So I want to say this number is equal to 11. Yeah, it's 11. And the biggest number we can make with 4 bits is actually 15, and that would be if these are all ones, because then from 11, this one adds a 4 because that's the fourth, the 4. So this is like 1, 2, 4, 8. So because it's a binary, and yeah, and so we'll just change this to 11 because that's what we're working with. We shift this once to the right, we're gonna get a new number, and that new number is going to be 0. Whoops, 0. There's going to be a 1 here, and then a 0, and then a 1. So notice this number, this is now a 0. We added a 0, and that's because we lost a number over here. We lost this one. This one has been booted out. We shifted everything to the right. So when you shift bits, you're gonna give up 1 bit and then replace at the other side with a 0 like that. And so this new number we get, so this new number should equal, if we do some quick math, 1 plus 4, and this should be 5. So if I'm not crazy, aliases or snippets working, there we go. Okay, so we just print out n just to see what's going on, and then we just run this. So we expect n to be 5 now after we bit shifted 11 one time. All right, let's check it out. Okay, here we go. It just took a second. So it's 5. There we go. And we got 5. Okay, cool. And so now we understand a right shift. We just say right shift over here. We go down a little bit more. Now let's do left shift. And the same concept, except it's just in the other direction. We're going to use the same number. We're going to use 11. And okay, so you can try to figure this out on your own what the new bits are going to be. But yeah, you can pause it if you want. But let's just dive right in. We're going to do a left shift. So that means this time we have 0, 1, 1, 0. Because we shifted all the bits to the left this time. That means the 0 goes on the right side and we lost this one. So now the new beginning is a 0. So we start from here now. And this new number, if we do quick maths again, it's 2 plus 4 should be 6. Let's print it out. And we get 22. Oh. Because we're working in 32 bits. So that means we don't lose a bit in the left shift. So that means what we really got is this number. We got 0, or we got 1, 0, 1, 1, 0. Because we put this bit in the beginning, and because our example is in 4 bits, but the computer is in 32 bits. So Java integers are always 32 bits because that is Java enforcing it that way. But if you're working in C, the size of an int actually depends on the system. So like if you're on a really old system, it could be like 16 bits or something. But those are usually not around. It's usually either 32 or 64. But we're working in Java, so an int is 32 bits, and of course we have extra space in the front. So if we do quick math this time, so this one represents 16, so that's 16. This is 4. So 16 plus 4 is 20, and then this is the 2 spot, and then we get, so that's 22. So we got 16 plus 4 plus 2, and that gives us 22. And so that explains this 22. When it comes to a right shift, that's not a problem because you can't like have bits from the beginning. I don't know if that makes sense, but that can't happen with a right shift. So anyways, now we understand how a left shift works. We just move the bits to the left and we add a 0 in the new spot that was created in the beginning. So now we know those 2 operations is really important for this problem. We need to know 2 more operations, and that's going to be and or. So sticking with the example, let's do an and. We're going to do this one. And so say we and these 2 numbers. Let's do 1, 0, 1, 1. So there is like a truth table to like understand these. Here we go. It's a little bit bigger now. So we have and. Two zeros make a 0 if we and them together. 0 and 1 makes 0. 1 and 0 makes 0. And then 1, 1 makes 1. So essentially, if they're not both 1s, they're zeros. Simple enough. And then the other one we have to know is an or. And an or is if they're both 0, it's 0. If at least one of them has a 1, it's a 1. Or both of them can have a 1 and it's still a 1. So it's like almost like the opposite of an and. So if there's at least one digit in the two bits, then it becomes a 1 when you OR them together. That's that. Back to our problem. We have 1 and 1. We AND them. That's a 1. We have 0, 0. That's a 0. And then 1, 1 again. It's another 1. And then we have a 1 and a 0. When we AND them together, that's a 0. Let's just go ahead and 8 plus 2 plus 1. So that's 11. We AND it with 8 plus 2 with 10. And we should get 10. All right, let's run them again. We got 10. Okay, let's do OR now, and we're gonna stick with the same numbers here. We're gonna OR them like that. And so the symbol for OR is this line down straight. I think it's like a pipe if you do bash, but so we're gonna OR these two together, and when we do that, we can do the quick math here. If it's 1 and 1, well, if there, okay, so with OR, if there's at least 1, then it's a 1. Or another way to say that is they're only 0 if it's both 0. Okay, so 1 and then 0, 0 is 0. 1 and 1 is 1. And then 1 and 0 is still 1. Okay. Let's do little system.out.print. We got, okay. Let's run them. Sanity check. We got 11. Nice. Okay, so now we know all the operations we need to solve this problem. So now we can finally get into it. So we're gonna go up here. We're gonna solve the reverse bits problem, and it's gonna be public. We'll just make it static void reverse bits, and it takes in a integer. And just to refresh what the problem is, we just go back to it real quick. Oops, not that. Here we go. Okay, there are two things that are important here. The first one is that it's a 32-bit integer, 32 bits. And then the second thing is our output is also an integer. So the input's an integer, the output's an integer. Okay, so reverse the bits. Here we go. This is our function. So it's not void, it's int. And the first thing we want to do, and it's not, maybe it is intuitive for you, but we're going to loop through, make a for loop. We're going to iterate 32 times, one for each bit. What we want to do, we're going to want a couple of variables. Well, actually, I think we just need one variable. We have a result, and we're going to actually set it to 0. We're going to initialize it to 0. And the first thing we're going to do in this loop with our result variable is we're going to shift it to the left. So we're going to do something like this. We're going to shift it to the left one time. And we put the equal signs here to like do it all in one, but all that really means is we are doing something like this, like that. So that's just shorthand. We put the equal sign over here. Okay, so what this does, we working back with our example, right? So we shifting this. So say this is the result, right? We shift it to the left one time, and then now we have 0, 1, 1, 0. So what we did just here is we made space for a bit to be placed at the end. So we're going to actually fill out the 32 bits of this. Right now, they're all zeros. But we're going to add one by one a new bit onto result. So we're going to basically overwrite 1 0 at a time. We don't want to lose what we wrote on the first position here. So that's why we bit shift everything to the left one time. And so the next thing we're going to do is we're going to have to figure out how to get the first bit of n. So this is a little tricky, but an example kind of helps. So if we want the first bit of n, we can say n is maybe 0. We'll just say 0, 0, 1, 1, 1. Okay. We have this number and we just want the first digit. So what can we do to make that easier for us? So what we can do is we can use one of our operations. And if you can guess which one, you're a genius. But what we're going to want to do is we're going to AND it. And we're going to AND it with 1. What does that do? So we're ANDing it with 1, and 1 looks like this in binary. And the result of that is whatever digit this is, it retains it. And it zeroes everything else out. So now we have 0, 0, 1 from after ending it with 1. And that's what we want. That is a way we can we can make sure we only have this digit here. We want it like this because the next thing we're going to do is we're going to OR this thing with our result variable with this. And what that does, it plops this bit right onto this position. So if we OR these two together, we get 0, 1, 1, 1. Essentially, we swapped in the bit here from n. See, this n, this represents the one that was originally on n over here. And we plopped it in the front, or I guess in the back of our result variable. So that's why we're shifting at the beginning, because we don't want to overwrite this new bit we just got. Okay, and so how do we do that in the code? It's a little unintuitive because it's bitwise operations, so we're not really used to working with those, but what that's going to look like is something like this. We have this OR sign equals, and then we can do parentheses, we can do n and 1, like that. So this also, another way to write this is this equals result or n and 1, like that. The same thing. So we're gonna AND it with 1 over here, and then whatever this is, we're gonna OR it with our result to plop that one digit onto the end here. So what this is actually called, a bit mask. And a bit mask is a way to pick out or modify a bit in a number. So bit mask sounds fancy, but really it's all it is a way to like do one of these operations on a binary number. So we're actually using 2 bit masks. We're using this one and this one, the AND and the OR. Okay, so we're gonna leave it at that, and then there's one more step to finish this problem. And what is the last bitwise operation that we haven't used that we learned? It's a right shift. We're gonna right shift n because we already got the number. So we're gonna take n, and we're gonna do n equals 1, like that. And what this does is, say if n is 0, 1, 0, 1, it becomes 0, 1, or it goes 0, 0, 1, 0. Because we already took this bit, so we don't care about it anymore. We're shifting it to the right, so we're throwing away that bit, and we're going to start with the new one on the next iteration of the loop. And then we're going to do that 32 times until we completely reverse the bits. The bits will be reversed because of this step. So we put the first bit from n on the right side, but when we keep shifting it one time to the left every iteration, the first bit is going to end up at the end. So we're going to end up reversing all the bits doing that. And the last thing we do is we're just going to return result. Okay. And to make sure we are not crazy, we can go ahead and copy that and post it in LeetCode, and we're just going to run it. See if we're not crazy. Nice, accepted. Let's submit it. Submitting, speeding up, and we got them. And actually, that is crazy. It's 1 millisecond, but 26 people. I don't know. Maybe 26% of people. I only beat 20%, 26% of people. Maybe you know what? It might be. I don't know. Some Optus super optimized C program or something. But what? Yeah, I don't think you can beat 1 millisecond anyway. So that's that. That's how you reverse the bits. Now you know you don't want to be the person who stumbles on bit operations. And so now we know we learned a lot of cool tricks. All right, this is Crispy Roo. Go ahead and subscribe if you want to. I'll see you next time.